Hi, this is Miss Hartwig. I'm going to give you an introduction to logarithmic behavior. What we're going to do is use everything you know about exponents and talk about how their inverse properties make a new function, or the inverse function, of logarithm. So what I've done is already, because we've been working on this so much in class, we've taken values that we've plugged in here as our x values going in as the independent variable. And we got these values out, and these were our values coming out, and we got this beautiful exponential increasing function. But there's some behaviors that we always watch for here, and I want to make sure you see them because they're going to play a role really soon as an inverse rule. So when we plug in a 0, base to a 0 power, we always get a 1 out. And whenever we plug a 1 in, whether it's 2 to the power or any base to a power, when you plug in a 1, you get a base out. So we have two occurrences that we can always count on. That exponentially, when you plug in a 0, no matter what the base is, when you plug in that 0, you're going to get a 1. And when you plug in a 1, you're always going to get the base. Along with that, we have another generality that we can bring up here. All of these values that we're plugging in all stand for powers. So we plug in these tiny little powers right here. These are all tiny little powers, and they come out as new, interesting numbers. And sometimes they're really big and sometimes they're really small. So we're plugging in a whole bunch of little baby powers, and we go base to a power, and we get, if we multiply that out, we can end up with a really, really big number. The same thing up over here, that when I plug in these tiny little powers, I get base to a power, and I might get a very, very interestingly small number out. And if you multiply it out, you won't even notice it necessarily as base to a power, but we have to keep that in mind because that's going to play a role this next time around. So a logarithm is the inverse of an exponent. And you know that if we're going to find an inverse is simply switching x and y. And it will be symmetric about the line y equals x. So if we just pop this line in here, because I want you to keep an eye on that, any inverse is where we switch x and y. And so the inverse property that we're talking about is that if I had originally y equaling 2 to the x power, the inverse is going to be x equaling 2 to the y power. And we're going to have to solve for y here, and I'm just going to have you hang on to that thought for a minute because honestly, you're so smart, you know that you can actually graph this thing already. You can graph and know exactly what this thing should look like because exponentially, we had this exponential growth here. And if we have all of these points that we already know, then the inverse should be just switching those x, y coordinates. So here we go. Right here we had exponentially, when we plug in a 0, base to a 0 power gives us a 1. So logarithmically, boom, we get this point, 1, 0. It's the inverse of 0, 1, we get 1, 0. The next point is 1, 2. If I have the point 1, 2, the inverse of 1, 2 would be 2 from the origin 2, 1. I also have a point exponentially that's 2, 4. 2, 4 would become 4, 2. And 3, 8 becomes 8, 3. In fact, even way back here, I got a negative 1, 1/2, so that's 1/2, negative 1. Negative 2, 1/4, 1/4, negative 2. And now we will approach the y-axis as an asymptote. Ooh, and I didn't do that so well, so I'm going to undo that and try it again. We want to get infinitely close, but not touch. Kind of hard to do with a big fat pen. But now let's talk about what really happened inside these mathematically. So here's our graph, and I've plugged in all of the numbers logarithmically. So we can look at our logarithmic growth here and look at what happened with our points. Now remember, exponentially we said when we plug in a 0 we got a 1. And no matter what the base was, when we plug in a 0 we get a 1. Well, look what happened logarithmically. if every exponent goes through 0, 1, then every logarithm is going to go through 1, 0. So we have our first rule of logarithms. That should make total sense to you, because every exponent goes through 0, 1. Every logarithm has to go through 1, 0. So no matter what the base is, log of any base of 1, gives us a 0. The next cool rule that we have is this fact from exponents, that when we plugged in a 1, we got a 2. This is a nice point right here. But in general, anytime we plug in a 1, base to a power is going to give us a base back. So we always had this point 1 base, just like we had 0, 1 a minute ago. And so if we plug in 1 base, if we find the inverse for 1 base, here it was 1, 2, the inverse is 2, 1. And so 2, 1 becomes our second rule that we can generalize and say, anytime we plug our base value in, we're going to get log base b of a base, and we should get a 1 back. That's pretty cool. Now, the next one is really a big kicker. So you got to pay attention, because remember we had all these tiny baby powers all in here. All these tiny baby powers. When we plugged in a power, we got base to a power out. So we plug in a tiny little number, and you got a big number out. So now the inverse is going to be true. We're going to plug in these great big numbers, and we're going to get a tiny little power out. So when we plug in these great big numbers, we're going to get log base b of a great big number, and we should get the tiny little power out. Now let's look at those. Take a second to look closely at what's happening here. For a 4, we got a 2 out. And for the 8, we got a 3 out. For 1/4, we got a -2 out. And for a -1/2 being plugged in the logarithm, we got a -1 out. So, if exponentially, when we plugged in our point as a little baby power, it was represented as base to a power, right here. And we would multiply it out and we get this big number out. And so keep that in mind, because the big number really should be able to be represented as base to a power. So how could you write 4? Instead of 4, what could we say? Well, 4 is really going to be, 4 is really 2 squared. And 8 is really 2 cubed. And look at 4 is really 2 squared, but what happened? Oh, the power came out. This is the little power. 2 to the 3rd. The 3 comes out. And in fact, it goes all the way back. What is 1/4? Well, that's really 2 to the -2 power. What is 2? 2 is really 2 to the 1st, and we got our 1 out. What is 1? 1 is really 2 to the 0 power, and we got our 0 out. So we have a rule that says that when you plug in a great big number, if you can write it as base to a power, then you're going to get your power back. And those are the 3 big rules to get us started in logarithms. And they all stem from using everything you know about exponents and using the inverse rule to make it into a logarithm. Now tomorrow what we're going to talk about is how do we take something like this equation and use logarithms to actually rewrite it so that it looks like this. And that's for tomorrow. So for today, you have taken an exponential function, you've graphed the inverse, and we've made inverse properties of this logarithm behavior by what happened exponentially. Good job.